Vivek Mukundan's talk yesterday, and I realized how advanced a seminar this is. And my talk is actually um, a talk on first principles. Um, so it's actually for those who are barely introduced to commutative algebra. And so I apologize to all the experts in the audience, which is probably everybody. Well, apart from enjoying mathematics by taking challenges, we enjoy the beautiful things of mathematics, and just because they're so pretty, and we learn to use these tools very often. And among the first things one learns in algebraic geometry from this beautiful book of Safarovich is the notion of a projection, of a projective variety. And on the algebraic side, the Noether normalization lemma, and its analog, the Weierstrass preparation theorem, and the completed situation. And these are things that I think no matter how much one is used to them, one really appreciates them because they serve us so well and we use it in our thinking all the time. And the topic that I want to talk on today is right next to that. It's intersection multiplicity. How does one count? How does one get the right number? Yeah. And this is a topic that has, I thought, perhaps not received an introduction after Serre's book on local algebra, which appeared in the 1960s, and I think most people of my generation learned from that. But I found myself wrong. There is an exposition in Eisenberg's commutative algebra with a view towards algebraic geometry. In fact, about an hour back, I pulled it out and noticed it was there. Well, anyway, that's what I'm going to talk about for most of this talk. Okay. There's a missing page here. So I'm starting with yes. So please forgive me. I'm talking as if we met all these definitions just yesterday. Yeah. So I want to talk first about intersecting curves in a plane. To start with, one would intersect lines and assume that the two lines are not identical. Then they either meet in a point or are parallel to each other. So one would say most of the time two lines intersect in a point, but there are those exceptional cases which can be remedied. So one has to understand what one means by remedy. One goes to the projective plane, and for each direction one adds a point. And now any two distinct lines meet in exactly one point. So one has some sort of conservation. We know this very well, and therefore we will work always in projective space, actually the projective plane. Okay, the next simplest case is when intersecting a line and a conic. So it's true that I should be writing down homogeneous polynomials in 3 variables, but I'm writing it in polynomials in 2 variables by setting the third variable equal to 1. So my notation is still that of the affine plane. So L is a line, C is a conic, and one is assuming that the equation for the line doesn't divide the equation for the conic, and they intersect in a finite number of points. So I have this picture here, which I call that's what I'm looking at. So a line and a conic meet in 2 points. Oops, I have to actually look at my other set of notes which seem to be missing. Okay, it's too bad. Okay, so a line and a conic don't always intersect in 2 points because they're used to lines and circles, and the line could be quite outside the circle. And quote unquote, we could refuse to look at real numbers and use only complex numbers, or use only algebraically closed fields. So a plane requires a field of definition, and a field of definition is an algebraically closed field. So in which case you have only two possibilities, assuming that the conic is irreducible. One is this thing that I've circled called case A, and the other is the case when the line is tangential to the conic. So in reality, there are of course more cases because the equation for the conic, the gxy, may not be irreducible. And so, yeah, there are various things that can happen, but which are, if anything, simpler to check. So let's concentrate on these two cases, case A and case B. The first one being when it intersects in two distinct points, and in the second where there is meeting tangentially in exactly 1 point. So, yeah, right. So the first case, which I call case A, is more frequent in the sense that if one proceeds algebraically, your line is, for all practical purposes, given by y equals px plus q. And so when I want to find the points of intersection, I substitute for y, and I get g of x comma px plus q. Yeah, it's too thick. I've got to do something about this. Maybe I can't. Okay. So that's the equation of it's a polynomial of degree at most 2, and which has a discriminant. So it has two distinct roots if the discriminant is non-zero, which is something like a b square minus 4ac, and which is almost never zero. I mean, yeah. We're working with complex numbers, so this, if I look at, it's not written down, but yeah, if I take a comma b comma c, I work in say complex 3 space, and I look at the zeros of b square minus 4ac. It's pretty small compared to the whole 3 variable space set of measures 0. So that justifies my saying the count is 2 almost always. Yeah. So which means if it's almost always, we should try to arrange things that it is always with the right definition. Okay, so that is, as I said, it's a question of more frequent. There is another way of looking at it, and that is to say that it is stable under perturbation. So for instance, if I leave the conic C alone and I were to perturb the line, and I don't know whether you see colors on my screen. I have colors. So the perturbed is in blue. Okay. So right, I'm looking at this picture here, where the conic has been left alone and the line has been perturbed from the original black line to the blue line. And if originally it were in two distinct points, in the new picture, in the blue picture, in the perturbed picture, it also meets in 2 points. Right? Now that is written in parentheses global here, but it is actually true locally too, meaning when we will consider higher degrees, which we will in a moment, we could perturb it in the sense, so this is the local picture. If you have two smooth things meeting transversely, different tangent directions, and you perturb one of them, it's still going to happen. They are still going to meet transversely in a point which was close to the original point of intersection. Okay, so there is no more to be said about that, except that you don't have to perturb only the second one. You could perturb both of them or one of them at a time. The answers are unchanged. Okay, so now let's go to case B, which was the tangential situation. And here, if you take the original line, which was tangential in black, and the blue line, which has been the perturbed line, you find that it intersects in two distinct points. And this also has to be taken with a grain of salt. After all, you could perturb a tangent line through a different point, no doubt. Yeah. So this is, once again, it is most of the time to be made mathematically precise in several ways. A dense set in your parameter space is the blue situation. It's not every single perturbation, but most perturbations, dense in the set of perturbations. Yeah. So it should give rise to 2 points. So that leads to this model that the perturbed picture gives the consistent answer. So the question is, how do you find out what the perturbed situation is without actually perturbing? Right? And Bézout's theorem answers that question. You know, while I speak, I'm also a little worried because I feel certain that, yeah, of course, that I'm speaking to an audience who knows 100 times this much, but what is beautiful even if we learned it 1,000 years back. Okay, so Bézout's theorem, what does it say? You've got two curves in the plane. And you know, I usually have much more hypotheses than are necessary, and I'm sure all of you know it. So I'm just keeping F1 and F2 irreducible so that there are no common components to make sure that the intersection is a finite set of points. The degrees of the equations are D1 and D2, and the number of points of intersection counted correctly is D1, D2. So that's the statement of Bézout's theorem, which is of course meaningless unless one explains the phrase what counted correctly means. Okay. So more precisely, it says somewhere I should have written that this number here is called the intersection multiplicity, right? So precisely what it says is that to each point of intersection, there is a natural number called the intersection multiplicity of C1 and C2 at that point, which I am denoting with a chi subscript P, C1, C2, the thing encircled in green right now. And when you add up all these numbers, you get D1, D2, okay? The product of the degrees. Yes. So this is, how do you compute this number? And algebra provides a very convenient way of doing it. It says you suppose they intersect in the point 0. So I've got two polynomials F1 and F2. So I'm talking about this part here. I've got two polynomials which vanish at the point 0 because 0, 0 is the point of the intersection. So there's no constant term. So if I take the polynomial ring and go modulo F1, F2, it's I get a K vector space. I'm thinking of this case the complex numbers. It's a non-zero vector space because I can evaluate the constant term. But this may keep track of too many points of intersection, and I only want to know what the contribution at the origin is. And so it's better to work with completions. So though localization will do. And it is the dimension of this vector space, which is a completely algebraic object. But it's something of a coincidence that this, well, something that requires the smallest degree of proof, that it coincides with the expected count. And what would the expected count mean? That if we were to follow our philosophy earlier of perturbing one of them, in fact, this is exactly what you would get. So I've written down the most elementary examples. Let's start with this one because we meet it in coordinate geometry in school or college. You take the x-axis and see how it meets a parabola. It's tangential, but you move the x-axis parallel to itself and you see it intersecting in 2 points if you are working with complex numbers. And if you look at y equals x cubed, yes, 3 points when you're working with complex numbers. Right? And on the other hand, there's number 2 and 3 in these two examples, here and here, are also the dimensions of the corresponding vector spaces, because the x-axis is given by y equals 0. So when I take this power series ring and go modulo y, I get k power series x. And then when I go modulo y minus x cubed, I've already gone modulo y, so I'm going modulo minus x cubed, so you get 3, sort of. Okay, so that's Bézout's theorem. And what's the higher dimensional generalization? Okay, so once again, forgive me, I'm talking as if we have just been introduced to this topic 5 minutes back. So, yeah, K is for all practical purposes complex numbers. This time we are taking irreducible subvarieties and projective space. And on this page, I've written things using hyperplanes. It's one way. A nicer way maybe to do as the beautiful way as shown by Safarovich, which is gone by projecting from a point outside X and repeated projections till you get a finite morphism. In any case, so let's run through this page. So starting from here. So if I've got an irreducible subvariety of a certain dimension and I take a hyperplane, and assuming X is not contained in the hyperplane, when I intersect it with H, the dimension goes down by 1. That's Hilbert's principal ideal theorem. And so most hyperplanes, in fact, do not contain X because there's at least one point of projective space which is not in X, and I can take a hyperplane through that point. So, and I repeat this, I intersect this with A general hyperplanes. And if, what is A? A is the dimension of the variety. Then I will be reduced to something of dimension 0, which means I've got a finite set of points. So, which means X intersected with this, which is a linear space of codimension A, I get a finite set of points. And for most linear spaces Y of that codimension, the number of points I get is constant, and that constant is the definition of the degree of X. So, right, so one has the notion of a degree of a variety. It's got D points. And then one is right to ask what is the analog of Bézout's theorem. So there we go. So if you take irreducible subvarieties of Pn of dimensions A and n minus A, which then have a good chance of meeting in a finite set of points. So here are the assumptions. Dimension A is that. I have to add this assumption to. I mean, one has to add it, of course, even if they don't have common components. Then one would expect that X and Y would meet in exactly D1, D2 points. This is not going to be true for the reasons, since it was not true already in the case of curves in the plane, but it would be true if you replaced Y by a general perturbation of 1. Okay, so we would expect that. We have not given an indication of a proof here. Okay, so what we want to do is to take this Y leave x alone, and then perturb the y, and then intersect and count how many points we get. So when you do that, of course, the new points of intersection would be close to the old points of intersection. And then what you would be doing is singling out each single P in the old intersection and see how many points there are close to P in the new. By new, I mean perturbed intersection. Okay, so this is written down with unnecessary precision here. Um, right, so and when I say close, we had better take the complex numbers or a field which has the topology, and we would be taking the usual topology, the topology dictated by that field. Okay. So, right. So you've got a point P on X, and this Y prime is a perturbation of Y. Yeah. And so I'm not intersecting X with Y, but I'm intersecting X with Y prime. And then I want to see how many points of those intersection are close to the original point P. So I fix a small neighborhood, and then I count how many points are in here. But everything in here is a little vague, because how do I choose neighborhoods and what is close, etc. So the exact meaning is actually given here. Well, perturbations, one should look at local perturbations and not global ones. But here we are in projective space, and the easiest way to perturb an object is to apply an automorphism. Take an automorphism of projective space. Yeah, so there is something in PGLN plus 1C, and replace y by sigma y. But then if I want sigma y to be close to y, then it just means that sigma is close to the identity, which means sigma belongs to a neighborhood of the identity, right? Okay, so in the interest of getting a stable picture, you would be taking u intersection and x intersection sigma y, hoping that it is quote unquote a certain number of distinct points. I have not used words like transversal intersection, but that is what is attained by when you take a maximum. And right, so you take this maximum, and then you take the minimum over W, because you allow sigma to get closer and closer to the identity. And then you also maybe have to worry about U, the neighborhood U, because otherwise you'd be keeping count. Yeah, your U may have been so large so as to include another intersection point of X and Y. So U has to be cut down as well. So when you go through this process, you're going to get the right number, which would be a geometric definition of the intersection multiplicity. Okay, now the simplest automorphisms, forget projective space of Cn, are translations. You can take any vector A in Cn, a point vector, and I can take translation by that. So that's an automorphism of affine space, which extends to an automorphism of projective space. And I take those automorphisms. It's good enough to restrict our attention to these. So the sigma that we choose are translations by A. Okay. So, and then, yeah, so I've got to, right? So then I want to see the collection, right? X intersected with Y translated is the same thing as saying X is equal to Y plus A, which means X minus Y is equal to A. So it's that, right? So I've got X. I've got to chop off the stuff at infinity if I want to define this map, right? If I want to define this map, so I've just called X prime and Y prime the intersection of X with the corresponding affine space Cn, like the first chart, let's say the 0th chart. So I have this difference map alpha, which goes from X prime cross Y prime to Cn, and I want to take the inverse image of A. Oops. So this is ineptitude with, yeah. So maybe I better not attempt anything in the, yeah. So one is taking the inverse image of A. When you do that, of course, you're going to get points. Well, your morphism is going from X prime cross Y prime to Cn. You're going to take an A. Oh no. Yeah. These things have various rules which have to be obeyed. Oh God. Okay. So A is in Cn and close to 0. I better chop it off. Okay. So first, let's see how does one find out how many inverse images there are. So we know this from field theory. You have the coordinate ring of affine space, which is here, which gets included inside the coordinate ring of X prime cross Y prime. And when you go to fraction fields, this is the finite extension, and the degree of the extension is the general number of, yeah, if I take most points of Cn and find out how many inverse images there are, I get a certain number of points, and the number of points is the degree of this extension here. The degree. The degree of this thing here. And degree, or which is the same thing as when you invert all non-zero elements here, which means, yeah, an S inverse construction going to the function field, you're just looking at the dimension of S inverse A tensor B over S inverse this. So it's, yeah, a vector space over the field of rational functions, and you're looking at its vector space dimension. That's the number of points that you get. That's the number of points that you get for most A inside X, inside in here. But we want to take the inverse images not all over, but only at points which are close to 0, 0. So for that, one needs convergent path series. And whatever number you get with convergent path series is the same as with formal path series, which is good because we are back to pure algebra, right? So you have this, let me turn back. You have this extension of rings here, and we complete it with regard to this. So I'm working with, we are going to the completion here and going through the same game. And so we get this path series thing here. Okay. And we are completing this one also, the A tensor B2 at the same point, because, yeah, there could, yeah, as been said before, there are other points of intersection that we are not concerned with right now. So the field extension at the complete local level is exactly what one wants. There's sort of irrelevant that A hat, B hat actually may not be integral domains, but they are always irreducible because there could be several branches passing through each of those varieties. Okay. So the number that you're looking for is the degree is that. Okay. So that's a purely algebraic definition. And that the rank, that's exactly what you're concerned with. Okay. So how does this compare to Bézout's theorem? As I said, this is something of an irrelevant remark, but maybe let's throw it in. I'm talking to an audience which are experts at commutative algebra, but for those who have not had commutative algebra before or are disinclined to it, I think this is a good motivation for Cohen-Macaulay. So you want to look at the rank of a module over a power series ring. Power series rings are local rings, and local rings, you have Nakayama's lemma, which allows you to compute the minimal number of generators of a module, and which is that number is of course going to be greater or equal to the rank of the module, right? So when you compute the minimal number of generators, you get back this thing here, which is exactly what you would have got in Bézout's theorem. Okay. So the simple way of counting, which is the thing here, that's what works in Bézout's theorem, but it doesn't work in general because this module is in general not a free module over the power series ring. In fact, it is free if and only if both the varieties that you're intersecting are Cohen-Macaulay at that point. So, yeah. And as we have seen, counting the length by using the minimal number of generators is greater or equal to the correct length. And the correct length is definitely the correct length because that is what you get under perturbation. Okay. So this E0, what I've called E0, this is the intersection multiplicity, being right of x and y at 0. It's essentially Chevalier definition. I confess to not having read the original, but Chevalier defined the Chow ring, and then he had to define the intersection of two cycles, and one would be using this number here when you want to define how two cycles intersect when they intersect properly. So though I've started with intersection multiplicity, there is actually a more basic concept that I should have started with, namely multiplicity. Okay, so yeah, the Hilbert-Samuel polynomial, as we know, is defined in the following way. You start with a local ring, a finitely generated module, even though we might, the case of interest is when the module is the ring itself, and you have an ideal which is contained in the maximal ideal. It's not been written exactly like that here. And you assume that m mod im is finite length, and then you look at m mod I raised to hm. That's a function of h, and which, as we know, is a polynomial, the Hilbert-Samuel polynomial, for h sufficiently large. And a polynomial of a certain degree r is, when you're working over a local ring, is the dimension. And the leading coefficient in this sense here is the multiplicity. That multiplicity itself has a geometric interpretation in the sense of perturbation and the sort of things that we've been discussing. So let's get into that. So yeah, this is, sorry about this. I've been writing as if I'm writing a textbook, or yeah. So if I replace I by another ideal j such that both of them have the same radical and I contains j, so first one sees both these things, that if I were to take the length of m mod j raised to hm, I get something of the same degree because of sandwiching, and an obvious inequality which tells me that one multiplicity is greater than the other. And this thing erased unintentionally. Yeah. Okay, that does two things for us at one stroke. And this is the sort of thing, I think, which can be found in Zariski and Samuel, right? Let's work not with just arbitrary local rings, but let's work with, in fact, power series rings over complex numbers, let's say, even convergent. And then, so for the module, we take the ring itself. And so this ring has a certain dimension R and a certain multiplicity obtained by looking at the leading coefficient. And right. So for any, if its dimension is R, you can find what is called a system of parameters. You can find some U1, U2, UR contained in the maximal ideal, which, which I'm calling J, which gets finite length. Right? And that multiplicity with respect to J is, it's just easily seen to be the rank of the module. So let me just say it in words. Right, you have this ring A, and you have some elements U1, U2, UR, which cut out something of finite length that turns, so I can think of it as a module. I can think of your original ring as a module over this, or an algebra over that, by sending the uppercase xi to ui. Right? And so you get a finitely generated module, and you find that, it is the rank which determines the leading coefficient, right? And which is the multiplicity with respect to j. And that multiplicity would have to be less than greater or equal to the multiplicity with respect to the maximal ideal. Okay? And there is a way of choosing, most, everything is general here. So if here I've written, it is well known. So that there is, okay, so for most j, again to be understood properly, in fact, you will always end up with this same number, you will get hold of E. So the statement is that if you take an arbitrary system of parameters, the multiplicity of the ring with respect to that is greater or equal to the original multiplicity of the ring itself, whatever the Hilbert-Samuel polynomial gives you. And in fact, in most cases, it will coincide with it. Yeah, yes, I sort of said that, forgetting that it was actually written down on the next page. So what I said aloud was this: you've got a complete local K algebra with residue field K. Assume A is a domain, then A can be expressed as a integral extension of a power series ring in several ways, but whichever way you do it, the degree would be greater or equal to the multiplicity, and most of the time it actually equals the multiplicity. So if you ignore the phrase most of the time, one says the minimum is actually equal to that. Okay. So that is what has been going on. So I'll have to go back by a couple of pages or three. So here A and B are the coordinate rings of two affine varieties and Cn, which meet in the point 0, and 0 is an isolated point of intersection. And I have this ring here, C, which is the completed tensor product. And we have this thing which I call alpha, the difference map from X cross Y. Maybe I can just go back a few. Yeah, I was talking about this map here. Everything is being applied to this map here. Okay, So this, of course, a talk should have started with really multiplicity before intersection multiplicity. And so I've just said what the relevant facts about multiplicity are in connection with geometry in terms of number of inverse images. And this is applied to the difference map. And so the difference map, yeah. So you take its multiplicity, and from what we are saying that this is a minimum, so the multiplicity, which is the going to be the intersection multiplicity of the two varieties at the point 0, has got to be greater or equal to the minimum. So what is the minimum? When you take a product of two varieties, and then the multiplicity is in fact just the product of the two multiplicities. So in fact, there's a better statement here, but you can ignore that. That's that. Right? So we wanted to make sure that each point of intersection gets does not get deleted, which means that the natural number associated to it is at least 1. And we are saying that the intersection multiplicity is greater or equal to uh, this product here. So yes. So not only is it a strictly greater than 0, you have a specific lower bound. I think this we can ignore. I inserted this page just to give an example to say what the multiplicity is in this example. And yeah, that it's attained most of the time, but not always. Okay. Okay. So I keep forgetting that notes actually have the conclusion, which I said aloud, but I'll read out again. So that's it. So this is what I said aloud instead of reading out faithfully from my notes. So x and y are two varieties, E0x and E0y are their multiplicities at the point 0. And the intersection multiplicity of x and y at 0 is greater or equal to the product of those two multiplicities. Okay. So this is completely in a geometric situation when one is working over a field. So let's go, we're entering the 1960s era now. So we have Serre's definition. So Serre abandons the geometric situation, leaves power series ring over a field and goes to arbitrary regular local rings, which are the next best thing. Then you have subvarieties. Well, he works with modules. Yeah. So subvarieties are replaced by modules. And to say that the closed point is an isolated point of intersection says that he's got two modules, M and N, and the tensor product has finite length. Okay. He defines the intersection multiplicity as follows here. This makes sense only, so you see some appearance of tors in the formula, so we require only finitely many tors because regular local rings have finite homological dimension. This is well explained by Serre in his book using the causal complex. Okay. But it is good to know where this thing comes from. So it comes from Grothendieck, who worked with groups of locally free sheaves and then coherent sheaves and used finite homological dimension to say that that's an isomorphism in the regular situation. But then vector bundles, locally free sheaves form a ring under tensoring. So this has an induced ring structure, coherent sheaves, despite the fact that M tensor N, it's not an exact functor. So when you work it out and go into what these days is called left derived, you end up with this formula. Now, if M tensor n is finite length, all these things have finite length. I mean, so that's the definition. Now, this is a purely algebraic definition, and things are not clear anymore why this number should be non-negative. And then it should be positive. So I'm pretty close to being out of time. So the first thing to be said is that in the familiar situation, by which I mean the geometric situation, this is no different from Chevalier's definition. And for that there is, it's easy. So there are two steps. First is an easy lemma, is to say that if R is regular local and you have a finitely generated module, there are two things you can do. One is this. You can take the alternating sum of these lengths here. Or on the other hand, you can take the rank of Z. By the rank, again, just to repeat, it means I tensor Z with the fraction field of R and take its vector space dimension. Okay. Now these two things have to be the same. Simply because under short exact sequences, 0 to Z prime to Z to Z double prime to 0, the rank adds up, vector space dimension adds up, and these things on the right hand side, they add up too, because there are only finitely many terms and the short exact sequence gives rise to, of chain complexes gives rise to a long exact sequence of homology. There are only finitely many terms. Great. So they're both the same. So, right. And on the other hand, if I take any Z, I can take a resolution by free modules. And free modules are, So in fact, there is only one module you need to check it for, and that is the ring R itself, because a free module is just a certain number of copies of R. And for the ring R, the rank of R is 1, and all these stores vanish except for I equals 0, where you get 1. Okay, so it's it comes down almost immediately to Chevalier's definition. I left it at this point, and then I sent my notes to Chris Scarlett, who said, I seem to have forgotten to say the thing below this green line here. That, yes, I did forget to say that. That when you want to compute tori in a geometric situation, you have this. You have tori R tensor R over K, A tensor B, comma R, and where R is an R tensor R module, like geometrically is the diagonal, and whenever something is given by a regular sequence, you can compute it using a regular sequence. So things like xi tensor 1 minus 1 tensor xi, which were called zi on an earlier page. So it's just that. Okay. So far we have found agreement between the geometric definition and Serre's purely algebraic definition. So as I said, we are in the 60s. And so what were Serre's theorems? In the geometric situation, we know exactly what's happening. So his assumptions are, as on the previous page, a regular local ring. You have two finitely generated modules M and N, and M tensor N is finite length. So, so first thing is this assumption already implies that the sum of the dimensions is less than or equal to the dimension of R. In the geometric case, we would have no way of doing it, or there was no way of doing it earlier, besides like taking products of varieties and using a diagonal. The thing is, we don't have products anymore. Yes. At least we can always take products over a field. If you take products over something like periodic integers, dimensions don't add up, excuse me. Okay. So he says this is always true. And then he said, if you work with regular, first of all, it's easy to see that proving it for a regular local ring is proving it for its completion. So you need to consider only complete regular local rings. And it says, for instance, take a discrete valuation ring like p-adic numbers or a finite extension of p-adic integers, the ring of integers in a finite extension, and take power series ring over that. Then he says, in addition, if the dimensions don't add up, if they fall short, then the intersection multiplicity is 0. When they do add up, it's positive. This is what he proved. And then he conjectured that, that whatever he proved, theorem B, this here, holds for all regular local rings. Okay? Those were his conjectures. So what did get true is the following. The first advance was in 85, simultaneously, I think, by Gillet and Soulet, who proved the first part, that is this part here. This is the part that was proved in 85. Oops. Yeah. By Gillet and Soulet, and also by Paul Roberts. The Gillet-Soulet approach is something that I would find it simpler to talk about. So this is a game where one converts modules into complexes of free modules. And so when you've got two modules, M and N, you replace them by their resolutions and you tensor them. Right? And you have these power operations, these Adams operations, which keep track of the codimension in which cycles live. So there is the Riemann-Roch theorem of Grothendieck, which amongst other things asserts that the K theory, but this has to be now said in a localized sense, keeps track of codimension, the Adams power operations. So Gillet insulated that carefully, and quite easily showed that if the dimensions don't add up to dimension R, it simply had to be 0, because the relevant part of M would be the power operations would, yeah, say the second power operation would take it by 2 raised to little a, which if a is the codimension of M, and 2 raised to b if b were the codimension of n. And if the a plus b don't add up to n, you can't see it, because over the maximal ideal, there's only one module there, and you know what it is. That's the closed point, which has codimension n. So that's how that proof went. Later, in 2000 or so, Olaf Gaber, showed not quite this, but he said that it's never negative. So it's greater or equal to 0, was proved by Gaber. And there were special cases done by Datta, Shankar Datta, which I have not mentioned, but in fact, both Chris Scarlett and I think learned a lot by going through one of his papers very carefully. I can talk about his result later. Okay, so it stayed there. And Chris Scarlett, this was his PhD thesis. He went back to the case that Serre had considered, which is this. Serre showed that the intersection multiplicity is positive, but Chris proved more. He showed that the geometric lower bound, which is that, is in fact valid. And so in wherever Serre showed that it was positive, so in fact Chris obtained this lower bound. And And then 4 years later, he made a further improvement. Excuse me, not improvement of this statement, but so generalize theorems of Serre in two different directions. One was to obtain this lower bound, and the second was to prove whatever Serre proved, this time for power series rings over a regular local ring of dimension 2. Okay, and so that's the sort of end of my lecture, and I'm sorry for giving, talking about material that many of us know very well from our younger days. Thank you.
So thank you, Professor Nori. We are now open for questions. Are there any questions or comments? People can open their mic and speak.